We were able to couple this idea of something that's coordinated and uncoordinated to create these soft and hard regions in the material.
Welcome to Nano Matters, the podcast that explores specific examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is LaShanda Korley, Professor of Materials Science and Engineering at the University of Delaware. LaShanda takes inspiration from nature to develop smart materials. So LaShanda, I understand that you find inspiration in all aspects of nature. Is it true that you were inspired by a worm?
Absolutely. Since graduate school, I have been amazed by the wonders of nature, specifically as a muse to design new material systems, an extreme focus of my group, especially around mechanical properties.
What was so special about this worm, and why did you think it would be a good basis for a new material?
The polychaete worm, or bristle worm, is a common marine organism. And one of the fascinating features of this particular worm is that the jaw displays a shift from very stiff to very soft mechanics down the length of the jaw. This allows the bristle worm to actually capture prey. So we were really interested in thinking about mechanical properties, especially gradient mechanical properties. So can you, in a single material, go from something that is very stiff to very soft? And we were inspired by this particular marine organism because it utilizes a supramolecular component through metal coordination as a way to derive these variations in mechanical properties. So we were quite interested in thinking about some of the tools we have in our lab, this ability to couple dynamic and static network systems as a way to create new materials.
So you mentioned the features of the jaw. How were you able to replicate that?
So to mimic this behavior in our particular system, we utilized metal coordination of a supramolecular polymer. So we utilized that and confined it in a system, a more static, covalently cross-linked material system, to fabricate what's known as a semi-interpenetrating network. And this way, you're able to utilize the confinement to control the dynamics of this particular system. And then we used these metal coordination with a ligand, and we utilized solvents to drive the metal down the length of a particular film. And utilizing this, we were able to couple this idea of something that's coordinated and uncoordinated to create these soft and hard regions in the material.
Can you discuss where you might use a material that has these hard and soft regions, and what potential applications might this type of material be used in?
Sure. So while our efforts are quite fundamental in nature, there are some key aspects that are relevant as you start to think about new technological applications. So we're quite interested in how local environment changes architecture and mechanical properties, and how we can utilize different binding motifs and binding strengths to dictate nanoscale assembly. So these are still areas of fundamental exploration that allow you to get spatial control in response to different stimuli. But we believe that this understanding from the systems that we are constructing will allow us to think about better shape memory materials for things like actuation and also for soft robotics. You can envision material systems that need something that is soft at one end. So maybe if you want to connect to tissue, and then hard at another end if you want to connect to bone. So there are some clear biomedical applications that would be directly related to these types of fundamental material properties.
You mentioned actuators and soft robotics. Is that looking at applications in prosthetics and robotics?
So, absolutely. I think you can start to think about material systems. Although we, again, work more on the fundamental side, we have an interest in trying to think about what are the application spaces and how can we create the different material platforms that we can potentially partner with others to think about. So from the standpoint of soft robotics, being able to generate material platforms that you can interface with existing robotic structures to create a more lightweight structure. So something that responds to different stimuli so that you can get, say, contractile motion as you control the interplay between soft and hard in these materials.
Are there other creatures or materials in nature that you've studied in your career?
So a longstanding interest in my group started when I was a graduate student is in spider silk. So we're quite interested in understanding the architecture and chemical makeup of spider silk, not to specifically mimic spider silk. There's a lot of fantastic research in that area, but to be able to extract some interesting information from spider silk as a way to replicate some of the features, things like supercontraction, the toughness enhancement that you achieve for commodity or conventional polymer systems that we make in my lab. We also have work that's inspired by seed pods. These are hygromorphic bilayer materials. These are materials that will respond to water or humidity and open and close much like the pine cone. So we've generated some material systems that mimic that bilayer actuation for new material development.
LaShanda, thank you so much for taking the time to talk with us today. Do you have any closing thoughts that you would like to share with our listeners?
For those who are interested in this idea of nanotechnology and biomimicry, my biggest takeaway is that we have nature all around us, and we can use that as a lens to inspire us. Nanoscale features are prevalent, from everything snowflakes to butterfly wings, and it gives us an opportunity to imagine, dream, and innovate. So there's a lot of innovation that can take place based on just exploring and observing nature.